we start this slowly. We started from the ideal impulse response. Okay? We started from the ideal impulse response and we take the low pass filter design as our example. We ever want to design a filter so it has exactly flat response in the pass band, that is from DC to a cutoff frequency, and 0 after that frequency. This is an ideal low pass response. If this is the desired response, which is 1 for the pass band, 0 over. Let me just say it's not actually the actual value. Okay, we need to put on the magnitude. We know that the inverse transform cannot be implemented. Inverse transform is going to be infinitely long on both sides. It's infinitely long on both sides, which is a distinct function in the time domain. So, if this cannot be implemented, so we suggest that we have an idea to just keep the middle part. Okay? To keep the middle part, that is, we will just keep the middle part from time minus n to plus n. And we are going to cut away, throw off the tail. Okay? We're just going to abandon everything that's outside this range in time, from minus n to n. Just keeping the middle part, and we know that the result is going to be the resulting filter. Of course, now it's an FIR because we have finitely many samples. Okay? Now, let me just remind you how a regulator summarizes again. Like, what is a filter? Filter is something that you convolve with your signal in time. You're going to use this filter, okay? By calculating the convolution of this filter with the signal in time domain, not in frequency domain. Is that clear? You can filter, now after this truncation, we said, or another way to refer to this process is actually truncation. To truncate, meaning that we throw away the part that's beyond the range, to truncate, okay? So the effect of this truncation is that if h of n is ideal, then we are essentially, what's my notation? So let's say this is LP, okay, that was my notation. The ideal low pass filter is denoted by HLP. And then the LP here is the corresponding impulse response is infinitely long, so we need to make a truncation. Okay? So by the product truncation can be expressed as, now we have designed G of n. This G of n is defined as the ideal response times a window function. A window function, and here we have an example of using the rectangular window, which is 1, which takes the value 1 from minus n to n, and 0 elsewhere. Okay, so after this truncation, we have a finite length. We have something that has a finite length. And we're going to use it. Okay, we're going to use it essentially. But wait a moment. Strictly speaking, this after this truncation, we have non-zero samples for the negative time, for n smaller than 0. Okay, so strictly speaking, this GFN, the filter, is not yet causal. Okay, so just to play safe, let's just to be rigorous, let's say this is step 1. We want to keep the middle part. Step 2 is just shift everything to the right. So our final design, this is our final design. Okay, our final design will be G shifted to the right by n samples, so that we have some non-zero values. So the new time index is 0 right here and 2n over there. Okay, and the total length of this filter is 2n plus 1. So far so good? Okay? So this is our filter. But we know that now the next thing is to discuss the effect. How much then is our frequency response? How far does it deviate from the ideal response? That's the question. So an important question. How far does the result of our design deviate from the ideal response, which is H/T. Or should I say, how much does this differ from that? Okay, that's a big question. Put a question mark right here. But so last time we talked about actually we just separately consider step 1 and step 2. The effect due to step 2 is pretty straightforward. When we shift the filter to the right, then the frequency response has a phase turn. Okay? So shifting to the right, there's a shift there. Magnitude response is not going to be changing. The magnitude response remains the same after shifting. Is that clear? Shifting does not affect magnitude response because it only introduces the phase turn. Is that clear? So this is quite easy. Okay? The effect is a phase turn, e to the minus j omega n. So the magnitude response stays the same. That's important concept. Okay? I hope you understand. And so let's just consider. So for now, let's not worry about causality. Okay? Let's say we are going to talk about how far does G. How far does G, the new magnitude response, differ from the ideal response? Okay, because the magnitude response of H is going to be exactly equal to G. So we don't need to worry about that. So how much does G differ from the ideal? So we know that, so last time we spent the last part to talk about the convolution of the second kind. Okay, this could be quite confusing. I want you to raise your hand to be very clear. So here, we are designing a filter, and eventually we're going to use the filter in the time domain by convolution. But in the process of designing this filter, we are doing multiplication in the time domain. And that causes convolution in the frequency domain. So that could be confusing, isn't it? Because the effect, now we have a convolution in the frequency domain, but wait, this filter, after our design, we're going to use this FIR filter in the time domain, so the convolution actually happens in the time domain. So I want this to be really clear. Okay, we're designing a filter, and the filter eventually will be used in the time domain by convolution, by taking convolution of this filter with your signal. Okay? Any questions so far? So do not be confused that now we're talking about convolution of frequency domain. Only for the discussion of the effect, to discuss the effect, how far, to answer this question. We want to discuss convolution of frequency domain only to answer this question. We want to know how far the result of our design differ from ideal response in the frequency domain. Okay? That's the only purpose why we ever mentioned convolution in frequency domain. Because why? Because our design method is very naive with the case of this. Our design method is to simply multiply the ideal filter with a window function. Okay? And naturally, the effect in the frequency domain will convolution in the frequency domain. Is that clear? Is that clear? Okay? Now can we continue? So last time we talked about now we are, let's say, since our G of n is a multiplication of our ideal response with the window function. Therefore, the effect in the frequency domain will be convolution. We are going to convolve our, let me use this equation. Okay, we are going to take cyclic convolution in the frequency domain because that's what's going to happen in the frequency domain. The result is a spectrum. Okay? The resulting spectrum is a convolution of two spectrums. One is the ideal spectrum, ideal low-pass response. The other is a Fourier transform of our window. Okay? So it turned out that, and actually this is your homework number 6. Okay? In your homework number 6, you are given a chance to mathematically write that the DGFT of our window is such and such. It's a digital sync function. Well, so I'll just yeah. So in homework 6, you'll learn that doing a manual derivation that indeed the Fourier transform of our rectangular window is going to have this form. It's something like sine. I reverse it down. I might be wrong, but anyway, you can check. It has a closed form. That's all I'm going to emphasize. Okay? It has a closed form. This is your, I put a question mark, something like this. It's a sinc function. Okay? It has a closed form that you can derive. So for our window function defined over there, if we have a rectangular window which lasts from -n to n, that its Fourier transform has a closed form expression. Okay? And so if we draw a kind of a sketch of this function, you draw a sketch of this function, you'll note that it has zero crossing. Okay? The zero crossing is when omega, when this angle equals to what? To pi, right? So the first zero crossing will be at omega equal to something. Okay, so there is going to be zero crossing, and then this function actually goes to negative because of this sign here. Okay, so it actually goes to negative. But if we take let me just draw. It goes from positive to negative. So this is going to be the Fourier transform of our window. So far so good. Now let me just mention that this width sometimes, or 2 times it. This is the main lobe. This first lump of region where the magnetic response is positive is called the main lobe, the main lobe. And all the others are the side lobes. These are good terminologies which you will be familiar with. And the width of this main lobe, we say the width of the main lobe is denoted by delta omega. Okay? If the width of this main lobe is denoted by delta omega. Roughly, delta omega is inversely proportional to the length in time. The longer we have in time, the narrower our main lobe is. Okay? So now, when we consider the convolution, this is in the frequency domain, okay? So now we consider we get back to here. Okay? So by the way, this every Fourier transform for discrete kind of signal is going to be periodic in frequency. Okay, please remember this is still true. Okay, so this thing here might show up again at -2 pi. That's it here. Okay, at +2 pi similarly. All right. So now imagine that we are going to make a convolution of this Fourier transform of our window. We're going to convolve this in the frequency domain with our ideal response. Right? And what is our ideal response? Our ideal response, let me draw a bigger picture. Our ideal response may look like this, a low pass filter. This is in the frequency domain. We have an ideal response, which is 1 in passband and 0 elsewhere. Okay? So I want you to imagine taking the convolution of this spectrum with this spectrum. Okay? So let me draw the main lobe a little bit narrower. Suppose that we now have a longer end. So we are going to calculate the convolution of this yellow function with ideal response, right? Which is to move the yellow thing around and calculate the total area of their product. Okay? So I hope that you can imagine, and we'll come back to that in the PowerPoint point. Okay? I hope that you can imagine, indeed, at least visually, okay? But imagine that the result will look like something that deviates from ideal. The ideal response is, let me just draw it with a dashed line, okay? If the ideal response is like square with super sharp transition. Now, after truncation, after our windowing, after we apply the windowing, the resulting filter has a magnitude response that has ripples, both in pass band and in the stop band. Okay, so the result is going to have a ripple, some kind of ripple and ripple. Okay, so we say that this result is going to deviate from ideal, deviate from ideal. Okay, so that's kind of where we were at from last time. The results of your design, and this is the end of your design, okay? You got a filter. You've gotten the filter, you should call it there. Okay? This is your design. Of course, it's not ideal. It has ripples. The frequency response is no longer a constant, okay? And no longer a constant, no longer zero in the stop band. So this is the design, okay? Now the question, any comment? Any comment? So let's come back to answer this question, okay? So how far does the result of our design differ from the ideal response? To answer that question, we may want to design to assign an objective function, okay? What's the total error? What's the total design error? How do you measure how badly or how well the design is? Right? So let me propose that let's define to answer that question. To answer that question, let's define a measure of total error. Let's define. Let's say if the result of our design is denoted by G sub m, okay? We add an m here because we have the length, because W has a length. Okay, so Gm, m stands for the length, m. That's all. Okay, now, so let's define an objective function which we want to minimize. Okay, so let's define our objective function, the total error, as E, which is if we consider from minus pi to pi, the design, how much does it deviate from ideal? How much does G, the result of our design, deviate from ideal, right? Deviate, so we take the difference. And what's the total energy at that difference? And we integrate over all omega. And we say this is an objective function. Is that all right? Which you want to minimize. You want to minimize. So under this definition, if we agree on this definition, then we can more concretely ask the question, how far does it deviate from ideal? Or can we improve our design by increasing m specifically? Right? So now the question, refined question. Now our refined question, pure prime. Okay, now our refined question, I want to ask for insight and opinion. Okay. If we increase m, right, this is something we can always try. Keeping more of the middle part. Okay, by keeping more of the middle part, do we reduce the total error? Do we reduce the total error? E, yes. Or no. Sign depends. You have 20 seconds to determine your answer. Okay? By increasing, giving more of the middle part, do we always reduce the total error, the design error? 1, 2, or 3. There we go. Equivalent, very good. Equivalent. Okay. E 的举手。How much say yes? Okay, very comfortably. How much say no? No. No, not willing to say no. How about depends? It depends. Why does it depend? 啊 ，intuition 就没有这么真的，not necessary。How about you？ 一样的 intuition depends。Maybe sometimes for certain end it's more optimal than others. You don't want to increase it. Really to increase it, you really need to increase it. It's possible, right? Yes? Raise your hand. No. Raise your hand. Probably not no. Okay, let's erase no. Okay? Asking you first. One is between 1 and 3. Depends. Raise your hand. Depends. Why does it depend? Maybe there's a particular M that's locally optimal. Okay? Locally optimal. Okay, is that what you mean? Yes, 同学，你解释为什么你会有？要大声一点。对，跟主办讲。You're talking about infinity. We are talking about generally. Okay, the answer to this comment is that when we increase n, the more we increase n, by increasing n here, more and more our result resembles the ideal. 越来越像 is similar. In what sense? Then my question is in what sense? Anybody yes? 再问一次 Yes. 你说为什么？Thank you. Any other? The answer surprisingly is a yes. Simply a yes. No, not. It doesn't depend. Okay, I'm sorry. It doesn't depend. The more n is, the lower e is. It's strictly decreasing function. The e is strictly decreasing function of n. And moreover, so yes, and moreover, we have when n approaches infinity, e approaches 0. Okay, and why is that the case? The result, do you have a clue? Why is this so wonderful? Why is it so wonderful? It's simply a result of particle theory. It's yet another application of particle theory. Let me show you one. Note that, do you remember that in the beginning of our semester I said Fourier transform is like a unitary transformation which preserves the norm, two norms after transformation. Right? So that means, maybe note that. Note that now we have two spectrums. We have two spectrums. If we divide E by 2 pi, the E divided by 2 pi is this. It's a total L2 distance squared, two norms squared, in the frequency domain. Okay? This is the two norms squared. In the frequency domain, we know that particle theory, the distance squared in frequency domain equals the distance squared in the time domain. It's a direct consequence of particle theory. Therefore, when we just keep going, we have n from minus infinity to infinity. Let's say n. Okay. So we have g n minus h of p of n total square. The total square in the frequency domain after integration is going to be equal to the total square in the time domain. Okay, so we covered it before. And therefore, now can you tell me why? When we increase n, because g, what is g? Because w is 1 between minus n and n. So actually G equals to our ideal response in the time domain from -n to n. Okay? So this is because of symmetry that we have. We can just count from n plus 1 to infinity. It's 2 times that energy. Now h of t of n squared. And of course, you can see that as n increases, this total energy decreases. It is wonderful. It's a wonderful result. A wonderful concept. Okay? Any comments? So far, so good? Strictly, if you increase n by 1, you reduce the total error by so much. Right? It's guaranteed. Okay, but if you think, okay, that's the end of the story, this is wonderful. So how shall we design? We should make our effort to keep them as much of the middle part as possible. If that's your thought, then I cannot say you're wrong. But there's another angle to look at how to answer this question. Okay, how far does G deviate from H? Okay, so let me just close this. So from the angle of L2 distance, from the perspective of L2 distance, yes, when we increase n, we always reduce the total error. Okay, but kind of interestingly, in a strange way, or strangely, if we define our objective function differently like this, I'll denote this by E infinity. Okay, there's a reason. If we denote our objective function, if we define it as the maximum error over all frequency range, okay. So if now we care about the maximum error, in our design, such as on top, I made a plot, right? So what, in this case, in my drawing, the maximum error seems to be right here, right here. Here we have probably a maximum error, maybe also here. I'm not actually here. Okay. So this is the maximum error, right? In this case, this is the maximum error over all frequency, such that the result of our design differs the most from the ideal response. Okay, right here, maximum error. We consider over the entire frequency range, that is from -5 to 5. Okay, and take the maximum error. The question now becomes, if we increase n, do we improve on this delta? Let me say that again. So now the new response, another question is that if we somehow design our objective function differently, we define it as such, the maximum error, okay, across all frequencies, then do we reduce this maximum error by increasing n? 1, yes. 2, no. 3, depends. Okay? And as a result, it's surprisingly, the answer is no. The answer is no. But in other words, no matter how long we increase the n, no matter how much more samples we are willing to keep the middle part, it would not reduce the maximum error. Okay, so this maximum error somehow cannot be minimized. There's another way to say it. Okay? This maximum error cannot be minimized. But so this is kind of strange, right? We know that the total energy is going to reduce to 0. But the maximum error does not approach 0. Okay? Or should I say more clearly, limit n approaching infinity is E infinity thing is not 0. Okay? Not 0. So what on earth is going on? The energy is going to approach zero when we increase length. But the maximum error does not improve. Okay? It's always going to be 18%, actually. 0.18. So this delta is nearly 0.18. No wonder how long you increase n. Okay? And this phenomenon has a name. It's called the Gibbs phenomenon. The Gibbs phenomenon. The fact that this error does not improve even if we are willing to make n larger and larger. This fact is called Gibbs phenomenon. It's exactly the same phenomenon, okay, if you will. Probably somewhere in engineering math, you have studied the Fourier series expansion for square waves. 方波的复列展开。I don't positive, I don't positive. And the fact that these errors does not reduce, does not approach zero when m approaches infinity. This is called Gibbs phenomenon. It's exactly the same phenomenon that we encounter in trying to expand to calculate the Fourier series expansion for square waves. In that problem, so like recall engineering math. So suppose that we have a square wave which is a periodic function for every, let's say every 2 pi. To make things simple. Okay, we have a square wave of some sort, 50% duty cycle, you will. Okay, 50% duty cycle square wave. And we know that by Fourier series expansion, right? We all learned that, right? This is a periodic function, so it can be expressed as a sum of cosine and sine, right? So then the result is, you should all know this, that what? It should be this function f of t is cosine t minus 1/3 cosine 3t plus 1/5 cosine 5t and so on and so forth, 1/7 and so on and so forth, right? Fourier series expansion. There might need to be a scaling factor. Okay, right? But we know that, so if we truncate this theory at a certain point, okay, only calculating the partial sum. When we only calculate the partial sum, what do we see? Remember, there's a Gibbs phenomenon, there's a Gibbs phenomenon over there. We see ripples and we see some sharp peak. Right? This is engineering math. Okay? And this is exactly the same thing here. Only the frequency and time domain is opposite. Now we have a continuous time. In there we have a continuous time signal, right? In here we have a continuous spectrum, the periodic spectrum, every 2 pi. Okay? So there we have Fourier series expansion. These are discrete frequencies. Discrete frequencies. And here we have discrete time. So like time and frequency becomes opposite. Okay, this is a dual situation, but mathematically they're exactly the same. We're going to show the condition. Does that make sense? Periodic spectrum for our case, a periodic signal for this engineering math, square wave. Continuous time for square wave, continuous frequency for our DGFT. Otherwise, the expression is exactly the same. We have to fix it on this. Nothing new. It shouldn't be new to you. Okay? Any comment here? Any comment here? Okay. So before I close this discussion, let me mention something. Let me mention that this Gibbs phenomenon is there. There is a kind of fundamental issue of trying to approximate a discontinuous function by continuous functions. Let me say that again. So if I have a sequence of continuous functions and the limit function is discontinuous. Okay? You will always encounter this phenomenon. That is, this is something in 宗教材. Something if you're interested, you should take advanced calculus. They offered by the math department. Advanced calculus or any such courses. We learned that the theorem is, let me just say for the case of the continuous time function, okay, is Fn of t are continuous functions, a sequence of continuous functions, numerous functions. And limit n approach infinity f of n. So we say if this limiting function, if this limit, if the sequence, if you take the limit of a sequence and this convergence is uniform, we have a uniform convergence. I'll explain what this is. If this sequence function converges uniformly to a limit, then the target function, the limit function, is also continuous. So this is a very basic property we talk about the convergence of the sequence of functions. Okay, there are sequence function that converges to the limit function, and if each of the function is continuous, and if this convergence is called uniformly, if they converge uniformly to the limit, then the limit function is also continuous. So let me tell you what is uniform convergence. Uniform convergence means if for any epsilon greater than 0, there exists an n such that for all n greater than or equal to n, we have fn of x minus f of x of t. The difference is going to be smaller than epsilon. The key point is for all x. For all x. So if these criteria is for any epsilon, however small it is, you can find an n larger, sufficiently large n, such that after that all the function does not differ from the limit by more than epsilon. And everywhere. The emphasis is on everywhere. Okay. Then this convergence is uniform. I want you to pay attention to and consider how does that differ from the definition of simply convergence. Okay? How does this definition differ from the very definition of convergence? How is it stronger than simply convergence? This is called uniform convergence. Okay? Is stronger than convergence. If you're interested, you can continue this discussion, okay? But then, if we agree that this is true, okay, and I said there's a theorem, we have no time to prove. There's a theorem that if we have all the continuous functions, the sequence of continuous functions that converges to a limit uniformly, then that limit function is also continuous. But wait, now we have a sequence of spectrum that converges to the ideal response. But we know the ideal response is not continuous, right? It's a ideal low-pass response. It's not continuous. Therefore, what's the conclusion? Therefore, this convergence will not be uniform. Is that clear? 有稍微有一种感觉吗 ？Therefore, the convergence is not uniform because our limit spectrum is not continuous. But each somewhere in the middle of the sequence, you take any n, the g of n is continuous. The limit is not continuous, so the convergence is there. Surely Gm converges to h of b, but h of b is not continuous, while every g of n is continuous. Therefore, this entire convergence process is not uniform. This convergence is not uniform. So how do we say something is not, the convergence is not uniform? Let's try to find the logical non-uniform convergence. So how do we define non-uniform convergence? Non-uniform convergence. The opposite of uniform convergence. So there are the different situations. Convergence, uniform convergence, non-uniform convergence. Okay? Uniform convergence, convergence. So this part is non-uniform convergence. Non-uniform convergence. How do you make the statement? How do you define non-uniform convergence? Let's try. Okay? How do we define non-uniform convergence? There is a sufficiently small epsilon such that non-uniform convergence such that for any n, however large it is, you can find x such that f at that place, let me say t, such that f at that place differs from the limit by more than epsilon. Okay? So this kind of describes the situation when the sequence converges to a discontinuous limit. Convergence is there, but the convergence is not uniform. Okay? So there must be some epsilon. It might be small. So for a sufficiently small epsilon, you can, however large n is, you can always find it somewhere in the frequency domain. Okay, in our case, somewhere right there, such that the difference is more than epsilon. So in our case, epsilon is 18. So in our example, epsilon is 0.18. Okay? So any epsilon less than that, you can always find a place in frequency, probably very close to the boundary. Okay? Probably very close to the boundary such that the difference is still greater than 0.18. Okay? So now that's kind of to wrap this over the entire story of the ship. Okay? Any comment? Yes, as always. Anybody who took that's out there? Anybody from the Communication Institute? 通讯所的举手。You should all take, consider taking the best calculus. Okay, so that's about it today. So next time, a preview. Okay, so actually now, so I hope that by this discussion, I've shown to you that there is some, the rectangular window does not do the job perfectly. Okay? Yes, it is optimal in a certain sense, but you simply cannot reduce this maximum error. Okay? So we need to think about something else. And that something else is other kind of window. Okay? By using some other kind of window, by designing our W N, we may be able to reduce this window. It's inevitable. It is inevitable, but we can try to minimize the maximum error. We can try to reduce maximum error by using different kinds of windows, something other than the rectangular window. And that's why we're going to touch upon next time we meet, next Tuesday, right? Next Tuesday.